permanent electric dipole having a positive charge plus Q at A and a negative charge minus Q at B separated by a distance 2A. A permanent dipole is one which has a dipole moment irrespective of the presence of an external electric field. The electric dipole moment P of the dipole is equal to 2AQ, directed from minus Q to plus Q along the axis of the dipole. Let the electric dipole be placed in a uniform external electric field of strength A, with its axis AB making an angle theta with the direction of the external electric field. Now, the charge plus Q of the dipole experiences a force F is equal to QE in the direction of the external electric field. And the charge minus Q of the dipole experiences a force F is equal to QE in the opposite direction of the external electric field. We see that on the dipole there are two equal and opposite forces along different lines of action, and hence we can say that the dipole experiences a couple which is the net torque on the dipole. This couple rotates the dipole until it is aligned with the direction of the external electric field. However, the net force on the dipole is zero, since it experiences equal and opposite forces. Since the net force on the dipole is zero, the couple on it is independent of the origin. The magnitude of the torque on the dipole is equal to the product of the magnitude of each force F and the length of the couple arm AD. The torque tau is equal to F into AD. Hence, tau is equal to QE into AD. In the triangle ADB, sin theta is equal to AD by AB. Since AB is equal to 2A, we have sin theta is equal to AD by 2A. Therefore, AD is equal to 2A sin theta. Substituting the value of AD in the expression for torque, tau, we get tau is equal to QE into 2A sin theta, or tau is equal to 2A QE sin theta. But the dipole moment P is equal to 2AQ. Therefore, we have torque tau is equal to PE sin theta. This is the expression for a torque experienced by a dipole when placed in a uniform external electric field. Since PE sin theta is equal to P cross E, we have torque tau is equal to P cross E. If the angle theta is equal to 90 degrees, sin theta becomes 1, and hence the torque on the dipole reaches its maximum. Tau max is equal to PE. Hence, we see clearly that the torque on the dipole is maximum when the dipole is held perpendicular to the direction of the external electric field. When the dipole is placed such that its axis AB is parallel to the external electric field, then the angle theta is equal to 0 and sin theta is 0, and hence the torque on the dipole is equal to 0. When the dipole is placed such that its axis AB is antiparallel to the external electric field, then the angle theta is equal to 180 degrees and sin theta is 0, and hence in this position also the torque on the dipole is equal to 0. From this discussion, we see that the expression tau is equal to PE sin theta will be valid only when the dipole is in a uniform external electric field. But when it is placed in a non-uniform external electric field, then the charges plus Q and minus Q of the dipole do not experience equal and opposite forces. Each experiences a force of unequal magnitude, say F1 on plus Q and F2 on minus Q, in different directions depending on the direction of the electric field strength at their respective locations. Hence, there is a net force on the dipole. In an external electric field of increasing magnitude, if the dipole is placed such that the dipole moment is in direction of the increasing field, then the net force on the dipole will be in the direction of the increasing field. Conversely, if the dipole is placed such that the dipole moment is in a direction opposite to that of the increasing field, then the net force on the dipole will be in the direction of the decreasing field. In general, the net force on the electric dipole depends on the angle made by the dipole moment with the external electric field. We know that when a dry plastic comb is run through dry hair, it gets charged by the method of friction. This dry comb can then attract pieces of paper. Here the pieces of paper are not themselves charged, but the electric field created by the charged comb induces a net dipole moment in the pieces of paper in the direction of the electric field. The electric field of the comb is non-uniform, and it exerts a net force on the pieces of paper having a net induced dipole moment. Thus, the pieces of paper move towards the comb because of the net force on them.